the previous session, we had discussed about the fuselage structures. Let us start off with fuselage loads in this session. Forces acting on the fuselage, which will be discussed in this presentation, are stress types, tension, compression, shear, combined loading, pressure, bending moment, and torsion on the aircraft fuselage. Let us start off with the stress types. Tension. Tension is caused by bending moment. For pressurized parts of fuselage, the hoop stress is longitudinal direction sums up for more tension in the fuselage. As hoop stress is the difference between the outside pressure and the cabin pressure. Tension is reacted by stringer and skin together. Material yielding stress is the limiting factor for the allowable stress. Stress type compression. Compression is caused by bending moment. Compressed areas causing buckling, which makes it a critical factor. Buckling is referred to as a material instability or structural instability. Compression is reacted by skin and stringers together. Material yielding stress and material buckling is the limiting factor for the allowable stress. Here you can see in the image the green mark are the result of compression or buckling on an aircraft. Stress types shear. Shear stress is caused by shear force and torsion, mostly reacted by skin. Shear is exerted when two tightened material tend to separate. It is the outcome of sliding one part over the other part but in the opposite direction. The rivets and bolts of aircraft fuselage experience both shear and tension stresses. Another stress type is combined loading. Shear stress and compression together cause combined loading. This results in combined load buckling. This panel over here taken from the fuselage is kept under for testing for the combined loading, where the green mark shows the shear on the component and the red shows the compression, due to which the wrinkles are formed on the fuselage part, which proves that combined loading also causes some damage to the aircraft fuselage. Stress type pressure. Circumferential stress is caused by pressure. Pressure stress is same throughout the fuselage, but it depends on the radius of the cross-section. Pressure is reacted by skin on circumferential direction and by skin and stringers in longitudinal direction. The limiting factor for circumferential and longitudinal stresses is to meet inspection fatigue, crack growth, and too big cracks. Bending moment. The bending moment My and Mz causes the fuselage to bend. Top part of fuselage is predominantly subjected to tensile stress, while bottom part is subjected to compression, or vice versa. The line that separates these two regions are called neutral axis, which always goes through the center of gravity of the cross-section. The fuselage cross-section can theoretically have non-symmetrical shapes. If the cross-section of the fuselage is symmetric along x and y axis, then the inertia along the x and y axis is zero. The direct stress is calculated along the skin and stringers as it is reacted on them. Total stress on the stringer is the sum of the total stress acting on the stringers and half of the two neighboring skin panels. This bending stress is converted in forces which is applied to specific parts. Later, the specific stress in the stringers and skin panels are calculated separately according to the applied force and material used. The maximum value will be acted on the top and bottom of the cross-section. The bending moment close to the neutral axis is smaller and zero at the neutral axis. The stringer and skin will experience different stresses, but strain will always be equal. Two forces are applied on each skin panel and two different stresses are derived for each panel. Shear. The shear force Y and Z axis causes shear stress on the fuselage. For a fuselage cross-section, the shear flow distribution in the skin which is produced by shear is ideally a single-celled closed section beam. Shear flow is applied to the skin by stiffness like ribs and frames. Shear loads and torsions are included simultaneously in load cases. Here we can see that the shear is acted more on the neutral axis near the neutral axis when compared to the top and bottom surface of the fuselage. Torsion force is a result of twisting force. It is caused due to wringing of skin due to pressure in air. Torsional stress in fuselage are caused by several ways, like torsional stress by engine torque on turboprop. Here, the engine torque rotates the aircraft in opposite direction to the propeller, turning the direction, which creates torsional stress in fuselage. Torsional stress on fuselage is also created when ailerons are maneuvered. Pressure. When a thin-walled or cylinder is subjected to internal and external pressure, a hoop and longitudinal stresses are produced. The fuselage is pressurized internally to create a sea-level atmospheric pressure inside. It is enclosed with pressure bulkheads in the front and rear ends in orthogonal direction. The pressure stress in circumferential and longitudinal direction is shown in the images here. This is the circumferential and this is the longitudinal pressure stress acting on the fuselage. Reduction in fuselage loads. Stressed skin with added stringers attached to the hooped frame reduces the bending stress acting on the fuselage. Frames gives the fuselage its cross-sectional shape and prevents it from buckling when subjected to bending loads. Stringers increases the stiffness in the skin under torsion and bending loads with small increase in weight. Pressure bulkheads are used to close the pressure cabins at both ends of the fuselage, which can take the shape of flat disc or curved bowls to reduce the pressure differences between the internal and the external pressure. I hope you would have understood about the fuselage design. Thank you.